Dear students, welcoming to the 10th lecture or 10th class of this session, in which the chapter power series solution of differential equations is studied. And in this class, we will go through the following sections or following topics. These are first Lagurre differential equation LDE, and then check its singularity, and after that power series solution was performed will be performed, and then Lagurre differential polynomials ln x. After the generating function for ln x will be calculated, then Rodriguez formula, and after that some reconciliation of ln x, that is Lagurre polynomials will be studied, and finally orthogonal properties of Lagurre polynomials will be discussed in this class. So go to our class, to the first topic, Lagurre differential equation. And the Lagurre differential equation is given by x d2y by dx square plus 1 minus x dy by dx plus ny is equal to 0. And I rewrite it as equation number 1 and wish to solve this equation by the method of power series solution. And to do this, we have to first check whether this equation is soluble or not in the method of solution. And to do this, we have to first recall the general form of the linear homogeneous equation, which is given here: p0x d2y dx square plus p1x dy dx plus p2x. And if we compare these two equations, then we will have p0x is equal to x, p1x is equal to 1 minus x, and p2x is equal to n. And since for the point x equal to 0, we can easily find that p0x is equal to x, and this p0x will be 0 for the point x equal to 0. That means at x equal to 0, this equation has a singularity. And since it has a singularity, then our next step will be check whether this is non-essential or essential singularity. If it is non-essential singularity, then power series solution will be workable, and if it is an essential singularity, then a power series solution cannot be workable in this case. So to do this, we have to first find out these values: x1, capital X1 function of x, that is equal to, we know that p1x by p0x, that is equal to 1 minus x taken from here, and p0x is here from here. So that is equal to 1 minus x by x, that is equal to 1 by x minus 1. Now capital X2 function of x, that is equal to p2x by p0x, and it is equal to n by x. The values of p2 and p0 are substituted from this to here. And now to calculate x minus 1, x1 at x equal to 0, that is equal to x into just write here the value of this x1, that is equal to 1 by x minus 1 at x equal to 0, and after calculation the value becomes 1, and that is finite value. And then x minus 1 square x2 at x equal to 0, this is computed here, and it is found that it is 0, and it is also finite. Since at x equal to 0, these values and these values are finite, these two values are finite, so this is the point x equal to 0 is a non-essential singular point, and therefore the power series solution of Lagurre differential equation can be possible. And now, since the presence of the term 1 minus x here, 1 minus x, this is not the method is not as usual what are done in case of Legendre, Bessel, or Hermite. So in this case, we have to use the method that is written here. First, we have to take x is equal to 1 by z, or z is equal to 1 by x, and from here you have to calculate dy by dx. Now dy by dx is equal, can be written as dy by dz into dz by dx. And after computation, here is the complete computation is given here. You have dy by dx is equal to minus z squared dy by dz, which is given in this box. And also now we have to find out the value of d2y by dx square, and the process or the method or the entire calculation is starting from here and it has ended here. And just look this, just go through these lines, complete calculations are given here, so it will not be very difficult to understand that the value of d2y by dx square ultimately becomes z to the 4 d2y by dz square plus 2z cube dy by dz. Just concentrate to these few lines, these and to work up to these, and go through all these lines, all these expressions, and it will be very easy to understand that d2y by dx is equal to z 4 d2y dz square plus 2z cube dy by dz. So our next job is to substitute the values of y dy by dx and d2y by dx square. Now in this case, since we have find out dy by dx and d2y by dx square, and these two values are now have to substitute in equation 1. That is equation 1 is here, that is Lagurre equation with what is given here. In this equation, just use substitute dy by dx square and dy by dx, and then you will have just go to that line. Yeah, here is that. It is written because x is 1 by z, so 1 by z, and d2y by dx square is here. Then 1 minus x was there, so 1 minus 1 by z will be here, and then the value of dy dx, and then ny is equal to 0. And here is simplification is done through this line and this line. Just separate this, and from this you will have these two terms from here, and from here z square dy by dz, and plus then will be plus z dy by dz ny. And after simplification, it will give z cube d2y by z square plus z square dy by dz plus z dy by dz plus ny is equal to 0. And I write this equation. This is equation 3. And now this is the standard form in which we can solve this equation, and as we used or as we employed in case of Legendre, Hermite, or Bessel's equations, differential equations. And to do this, we since we are using power series method, so y is taken as that is root to infinity a r z to the power n plus r. That is in this case y is in the ascending power of z. So from here dy by dz is equal to ar n plus 1 z into n plus r minus 1. And similarly d2y by dz square is can be calculated from this relation, that is sum over r ar m r m plus r n plus r minus 1 z to the n plus r minus 2. And now our job is to substitute these values of y dy by dz d2y by dz square in these relation, in these expression, that is in equation 3. And if we do that, then we will have from here z cube, here is the value of d2y by dz square, this is that, and z square dy by dz, and here z square, the value of dy by dz is here, and after that dz dy by dz z, here is the dy by dz, and finally n into y, that is r z to the n plus r. Just substitute these values. Here it is done here. And now our next motivation is to simplify as it can be written as simple as possible. So from this you can easily understand that this expression will give you ar m plus r, a plus r minus 1, and z to the power m plus r plus 1, since it is z cube and it is minus 2. The power is minus 2 here. So from after that r is equal to 0 to infinity. From here ar m plus r, z to the power m plus r minus r also here. And then after that from this you will have r is equal to 0 to infinity ar m plus r, z to the n plus r, and since z is multiplied here, and after that n into r will be 0 to infinity ar z to the n plus r. Now just combine these and these in a single expression, and these another single expression, and that will give you ar m plus r minus 1, then plus m plus r z m plus r plus 1, r equal to 0 to infinity ar m plus r plus n z to the n plus r, that is equal to 0. And from here you can write that m plus r is the common term from here, then m plus r from minus 1 from here, and then from here another plus 1. That is here, that is done here. And z to the n plus r plus 1, and then r is equal to 0 to infinity ar m plus r and plus n, because these two terms are combined here, this term and this term. So this, that is here, that is equal to 0. So from here you can write r is equal to 0 to infinity r m plus r whole square z to the m plus r plus 1, then r is equal to 0 to infinity ar m plus r plus n z to the m plus r is equal to 0. This is equation 4. Now equating the coefficient of z to the power m plus r to 0, we can write for the first case, since you are trying to find out the coefficient of z to the m plus r from these two expressions or two terms, then in this case r should be replaced by r minus 1. Then you will have from here a r minus 1, then m plus r minus 1 square, and from here a r m plus r plus n, that is equal to 0. That is, in the first term r is replaced by r minus 1. So from here you can calculate that this ar is equal to m plus r minus 1 whole square with the minus sign by m plus n plus r a r minus 1. This is equation 5. And using r is equal to 0, 1, 2, 3, etc., you can find out the values of different the different arbitrary constant a. So for first case, I have written or we have to first use r is equal to 1 here. So if r is equal to 1 here, the a1 is equal to m plus 1 minus 1, then m plus n plus 1 and a0, that is equal to minus m square by m plus n plus 1 a0. And in this way the value of a2 is calculated here, and just we have to concentrate here and just use r is equal to 2 in this expression, then you will get these into a2. And now we have to substitute the value of a2 from this into a2, and that is equal to it will be a2 is, sorry, it is mistakenly written as a2, it will be a1. So these and a1. Now substitute the value of a1 from this, and finally we will get, go through this, and finally we will get m square n plus 1 whole square m plus n plus 1 into m plus n plus 2 into a0. And in this way you can find out other higher values of s. And if therefore if you expand y from this equation, go to that equation here, given here, that is here, just here, look at here, y is equal to this. Now here substitute r from 0 to higher values, then you can write, you can get this relation y is equal to a0 z to the power m plus a1 z to the m plus 1, a2 z to the m plus 2, and so on. And here z to the power m is a common term, so 1 plus a 1 by a0 z, then a2 by a0 z square, and so on. And from here if you substitute the values of a1 and a2, this there is a1 and here is a2, here is a2. See here, a1 is this and a2 is this. Just use these two values a1 and a2 in this expression, and finally we will get a0 z to the m 1 minus m square by m plus n plus 1 into z, m square into m plus 1 whole square, m plus n plus 1, m plus n plus 2 into z square, and so other, and many other terms. So just use a1 the value of a1 as this and a2 as this in this relation, just substitute this and you will get it. So so y is obtained as this. It is equation number 6. Now use r is equal to 0. Now if you use just let this equation here, and now go to some previous slide. That is here. That is here in this expression. No, this in this expression. So in this expression right here, ar m plus r whole square z to the power m plus r plus 1, and this. And in this equation, if you use r is equal to 0, so that will give you a0 m plus r. That means a0 m square z to the power m plus r, and this will give you ar into m plus r and z to the power m. And it is written here. It is written here. A0 m square z to the power m plus 1, a0 m plus 1 z to the power m is equal to 0. And see here, the power of z in this expression are, for these two terms, are different. Here z to the power m plus 1 and z to the power m. So if this equation is to be satisfied, that is to satisfy this equation, so in that case this term and this term should be separately 0, and that's why if a0 n plus 1 z to the m is equal to 0, that is written here, a0 n plus n plus z to the m is 0, so you can write m plus n is equal to 0 because a0 is the first term and it cannot be 0. So from here you get m is equal to minus n. And now if you write m is equal to minus n to this relation, to this expression, that is expression number 6, in this case m should be replaced by minus n. So if you do that, then you will get a0 z to the power minus n, and all other terms. Just to look at this expression, and in that expression I have substituted m as minus n. That then you will get z is equal to a0 z to the power minus n, 1 minus n square by 1 factorial z plus n square n minus 1 whole square by 2 factorial z square, and all other terms. And since z is equal to 1 by x, just substitute z as 1 by x, then you will get y is equal to a0 x to the power n 1 minus n square by 1 by x plus n square into n minus 1 whole square by 2 factorial into 1 by x. Okay, just do this, just practice it, and I think there will be no problem to go to achieve or to go this line. And then finally from this you can write y is equal to a0 x to the power n, just multiply all these terms with x to the power n, and then the next term will be n square minus 1 factorial x to the n minus 1 plus n square n minus 1 whole square by 2 factorial x to the power n minus 2, and all other terms. And in this way the last term will be, say it is plus, then minus, then plus, so it will be minus 1 to the power n. And in this case, in this way n is increasing up to, and in such a way that the last term will be that will be here it can be written as n factorial. The last term will be n factorial. Just look at this and think the last term must be 0. So and why this last term is 0, that is explained here. Because from n square minus 1 whole square by 2 factorial, this is the common term x to the n minus 2. This is the second term, and that can be written as 1 n into n minus 1 by 2 factorial, 2 whole square by 2 factorial, and then x to the n minus 2. So in this case, see here that the second term. So in this case, minus 1 to the, this can be written as minus 1 whole square, minus 1 to whole square, then n factorial from here, and that n factorial whole square, and 2 factorial here, and x to the n minus 2. In this way, the last term of this series will be minus 1 to the power n in the last term, and then here will be n factorial whole square. Okay, and in this case, as it is increasing to n, so in that case it will be n factorial instead of 2 factorial. So it is n factorial here, and in this case, since n is increasing at this term 1 2 3, this term is increasing to n, so x to the n minus n will be the last term. So this will give you minus 1 to the power n, and then n factorial, and x to the power 0, that means 1, that is minus 1 to the power n factorial. So it is not, it is you very easily computed the last term as this, and I write this as equation number 8. So we finally get the relation, get the solution of Lagurre differential equation, what is written in this expression, that is in equation 8. Now go to the next topic. The next topic was Lagurre polynomial function in Lx. And Lagurre polynomial function, or only Lagurre function, is nothing but the solution of the Lagurre differential equation. Any solution of Lagurre differential equation is called the polynomial, Lagurre polynomial ln x. And as we obtained in the case of in equation 8, that y is equal to a0 x to the power n factorial 1 factorial n square by 1 factorial x to the n minus 1, then plus n square n minus 1 square by 2 factorial x to the n minus 1, and in this way last term is minus 1 to the power n factorial. And that is recalled from this equation. So no problem is there. So this is that is y is written in this way. In this way, not this is the solution for y. So now putting a0 is equal to minus 1 to the power n. This is the constant, and you put, or you take a0 as minus 1 to the power n, and assuming that n to be a positive integer only, and then the value of y, that is the solution that we will get, is called the Lagurre polynomial equation, or ln x, and that is given by, in this case, that will be given by the solution in that case, since the solution in that case will be called or as Lagurre polynomials ln x. So ln x will be written instead of y, that is equal to minus 1 to the power n, since a is taken as minus 1 to the power n, and the rest part then the rest part here is the rest part. Just write all this this expression here. This is equation number 9. Now putting n equal to 0, 1, 2, etc., you can easily find out the values of Lagurre polynomials for different order. And for case of n is equal to 0, you can calculate the zeroth order Lagurre differential Lagurre polynomials, that is L0x, and that can be calculated from this. And this from this relation, that will be minus 1 to the power 0, and from here, since n is 0, so from here 1, that is L0x is equal to 1. And then for n is equal to 1, then that will be give you L1x. L1x can be calculated from here, minus 1 to the power n, then x to the power 1, and minus n square by 1 factorial, and here will be x to the power 1 minus 1, that means x0, that is you will get from here 1. So that and after calculation you will get the calculation is given here. So that is there, L1x is equal to 1 minus x. And for n is equal to the value of the Lagurre polynomials L2x is computed here, and entire computation is given here. Just see this relation, just look at this relation, this expression, and using different values of n, you can easily find out all the values of L1, L0, L1, L2, and so on, and all the calculations are given here. Just go through this and you will understand. Now the next topic is generating function for ln x. Now the generating function for ln x is written as 1 by 1 minus t e to the minus x t by 1 minus t, and it is called the generating function for Lagurre function or Lagurre polynomials ln x, because that ln x can be derived from this term or this expression of this function. And here I have written here just this term 1 by 1 minus t to the minus x t by 1 minus t, and it can be written as 1 by t. Just expand this series, and that will give you 1 minus x t by 1 minus t, then plus x t whole square by 2 factorial 1 minus t whole square plus all other terms, and in this way the last term will be minus 1 to the power n x t to the power n in factorial 1 minus t to the power n, and so on. And from this you will just multiply all these terms with this term, that is 1 minus t to the power minus 1, and you will get this expression. Just do it, and here all computation is given completely without any missing of steps. So then now the coefficient of t to the power n can be given by the coefficient of t to the power n, and the coefficient of t to the power n will be the only just you have to look at this, and you can and the term or the coefficient of t to the power n will come from only this term. And for first term, that will be minus 1 to the power n. Here is minus 1 to the power n, then x to the power n by n factorial, and after that n will be decreased by 1. Since in this case n is increased by 1, and in that case no, for the next term, since t is multiplied will this term, and if you expand this in series, then that will be 1 minus n into something, n into t and other terms. So t will be for the second term will be multiplied with this, and then the power of t will be t to the n plus 1, and then t to n plus n should be replaced by n minus 1, and that's why you will get minus 1 to the n minus 1, then x to the n minus 1, and here n minus 1 factorial, and n is come from the series expansion of this term. And after that, in this way, the next term will be minus 1 to the power n is decreased another 1, so x to the n minus 2, then x to the 1 minus 1 to the n minus 2, then x to the n minus 2, then from here n minus 2 factorial, and then n, and the very next term will be n minus 1, and here is another 2. Okay, this 2, this is another 2. So in this way you will get, if you take as minus 1 to the n by n factorial as common term, then the left terms will be in this manner. Here is written the rest term was written here, and now this term is written here, and this is here, and just write n factorial as n into n minus 1 factorial, and this n is here and n minus 1 factorial is there, x to the n minus 1, and here also just write n factorial as n minus n into this n minus write as n into n minus 1 into n minus 2 factorial, because n factorial can be written according this expression. And then n minus 2 factorial is there, x to the power n minus 2, and the and this term is written here, and all other terms plus all other terms. So that will give you x, this is written here, x to the power n minus n, this will cancel each other, n square x to the power n minus 1, then n square n, and here is n square n minus 1 whole square by 2 factorial, these two will be written as 2 factorial x to the power n minus 2 and all other terms. So this is nothing but the Lagurre polynomials ln x. So ln x has computed or derived from the function 1 minus t e to the power minus xt by 1t. So it is the generating function of ln x. So 1 minus t e to the minus xt by 1 minus t, if you take all the terms, then it will be n is equal to 0 to infinity ln x by n factorial to the power n. It is equation number 10. Now come to the Rodriguez formula. We have dn by dxn x to the power n e to the power minus x, which is the nth order differentiation. Now to find out the Rodriguez formula, now we have to find out the d to the power n by dxn, that is the nth differentiation of the function x to the power n e to the power minus x. And if we do that, here we have to use Leibniz theorem. And you know that the Leibniz theorem, according to Leibniz theorem, the nth differentiation of this function will be first take x to the power n as constant. Here it is done, and then nth do or perform the nth differentiation of the second function e to the power minus x. That is done here, d to the power n dxn e to the power minus x. And then according to Leibniz theorem, the next term will come with a constant, that constant is given as nc1. This is the constant term, and then differentiate this e to the power minus x to one order lesser than that was done in the previous case, that is in this case. So the order of the differentiation in this case will be n minus 1. So d n minus 1 dx n minus 1 e to the power minus x, and then differentiate this term for the first time, that is n x to the power n minus 1, and then the next term will consist another constant which is nc2. Then differentiate e to the power minus x one order lesser than this that was done in this case. So d to n minus 2 dx n minus 2 e to the power minus x, and differentiate these x to the n for further one, that is the second order differentiation of this. That will give you, you can use from here n into n minus 1 x to the power n minus 2, and in this all other terms will come. So plus dot dot etc. And from here you can write that since differentiation is done or will be done to n times, so for each time of differentiation there will be a minus 1 form here. So for nth differentiation there will be n times of minus 1. So this will give you minus 1 to the power n, then e to the power minus x, and x to the power n is here. And from here you can write that in this case, since the differentiation is done here for n minus 1 times, so the term here will be minus 1 to the power n minus 1, and then e to the power minus x, and from here n into x to the power n minus 1, and you can write this constant nc1 as n factorial by n minus 1 factorial, and then plus on here you can write since it is the differentiation is here for the n minus 2 order, so for each term minus 1 will come, 1 minus 1 will come, and this will give you minus 1 to the n minus 2 e to the power minus x. Then from this n is here, and this n is here, and also from here this n is here, and n minus 1 is also here, x to the power n minus 2, and the value of nc2 is here, n factorial, then 2 factorial, then n minus 2 factorial, and all other terms. Now just to simplify, the first term is written as usual as it was in this case. The second term minus 1 to the power n minus 1, then e to the power minus x, then x to the power n minus 1, and this n is written here, and n factorial can be written as n into n minus 1 factorial, and in the denominator there is n minus 1 factorial, and then plus this term, these and these are written here. then x to the minus n minus 2, then you can write n factorial as n into n minus 1, and then here written here n factorial is written here n into n minus 1, and then n minus 2 factorial, and by 2 factorial and n minus 2 factorial, and this term n into n minus 1 is written here, and all other terms. So this will give you minus this term, the first term is here, and from the second term you can write this will vanish, this will cancel each other, so you can write minus 1 to the power n minus 1 e to the power minus x to the power minus n, and then n square. And from this second term, minus 1 to the power n minus 2 n square, n minus 1 whole square by 2 factorial x to the power n minus 2, because these two cancel each other. And in this way, finally you can take minus 1 to the power n e to the minus x as constant term, and the rest term are given here. And you know that this term and the term written in the third bracket is nothing but the Lagurre polynomials or Lagurre function. So d to the power n dx n x to the power n e to the minus x is equal to the minus x ln x. And from here you can write ln x, that is this is equal to e to the power x will go to this, and that will give you e to the x, e to the minus will, if you divide this to the minus x, then it will be e to the x dn dx n x to the power n e to the minus x. And this is equation given as equation number 12, and this equation is the Rodriguez formula, because any kind of ln x can be found out from this equation very easily. So let us do that. Different Lagurre functions can be calculated using Rodriguez formula as below. Here ln x, we know that ln x is given by e to the power x dn dx n x to the n e to the power minus x. Just use n is equal to 0 in this expression, you will get L0x, that is equal to 1. The calculation is given here, and then using n is equal to 1 in this expression, you will obtain L1x is equal to 1 minus x. And just remember that was also calculated in the using using the general expression of the Lagurre polynomials. So L1x is equal to this, and using n is equal to 2 in this expression, in this equation you can find out the value of L2, that is written here, that is computed here. All the calculations without any step missing is done here, and you just go through this, follow this, you will understand. Now recurrence formula, recurrence relations for ln x. The generating function for Lagurre function is given by as well as we have already seen that the recurrence, the generating function for Lagurre equation can be written as 1 by 1 minus t to the power minus x t by 1 minus t, that is equal to n is equal to 0 to infinity ln x t to the power n by n factorial. This is, I write it as equation for this section, and from this you can write e to the power minus x t by 1 minus t, that is equal to this 1 minus 2 will be multiplied with this term, so 1 minus t, and this term is here, and write it as, let this term is equal to omega, the right hand side is equal to omega. Say now so log ln omega, that is logarithm of this omega will be e to the power, since it is e to the minus xt, from this e to the minus xt by 1 minus t and omega. Just look at these two terms. So log omega will be minus xt by 1 minus t, and this can be simplified as this, and finally we get x minus 1 by 1 minus t. Just here nothing very difficult, nothing very absurd calculation here. So the log omega is equal to x minus x by 1 minus t. This is equation number 3. Now differentiating this equation, that is equation number 3, with respect to x, what you will get 1 by omega del omega del x, that is equal to 1 minus 1 from here 1, and if you differentiate this, you will get 1 by 1 minus t, and that will give you minus t by 1 minus t. This is equation 4. Now again differentiating this expression, that is equation 3 with respect to t, that will give you 1 by omega del t, that is equal to, just differentiate this term, that only differentiate this term, so minus 1 is here, and differentiation of this with respect to t is computed here, and finally we will get minus x by 1 minus t whole square. This is equation 5. Now from equation 1, that is equation 1 is here. Now from equation 1 you can also find out del omega del x. Now if you wish to find del omega del x, that is in equation, this is equation, no, it will be equation 2, from equation 2. From equation 2, del omega del x, just differentiate this term. That will be 1 minus t n equals to infinity ln prime x t to the power n factorial. That is written here. That is done here. That is done here. Yeah, that is done here. Del omega del x 1 minus t. That is 1 minus t n equals to infinity. This is equation number 6. And from equation 4, that is equation 4. You know that from, and you also see here from equation number 4 that del omega del x will be minus omega t by 1 minus t. That is also written here. Del omega del x minus omega t by 1 minus t. And now just substitute the value of omega. That is the value of omega is written in this form. This form, write thus. Just write this form 1 minus t and this term in place of omega in this equation. That is in this equation. If you do this after simplification, there all the calculations is given here. There you will get del omega del x is equal to minus t, n equals 0 to infinity, ln x t to the power n by n factor. This is equation number 6. Now just compare equation 6 and 7. The left hand side are equal. So the right hand side of both equations will be same or equal, and then you can write minus t. This is written first. Minus t n is equal to 0 to infinity ln x n factor t to the power n is equal to this 1 minus t sum over n equal to 0 to infinity ln prime x by n factor t to the power n. This is equation number 8. Now just equate the coefficients of t to the power n from both sides of equation number 8. Then you will get, since it is t and that will be multiplied with t to the power n, and this will give you t to the power n plus 1. So in this expression, n should be replaced by n minus 1. And if once you do it, then you will get ln minus 1 x. Obviously it is here, and then n minus 1 factor. This is also here. That will be equal to the first term is here 1 into this. That means in this case the coefficient of t to the power n will be ln prime x by n factorial. And here see that t will be multiplied this t to the power n, and that will result the power of t as n plus 1. So in the second case, n should be replaced by n minus 1 here also. And if you do that, then you will have t ln minus 1 prime x, that is here, and then here instead n factorial n minus 1 factor will be here. So this term is equal to this. Now the situation comes to simplify this relation only. So from here you write this as ln minus 1x by n minus 1 factorial, that is equal to ln prime n by x. Just simplify this n factorial can be written as n into n minus 1 factorial, and then minus n prime x, and this is written here, and n factorial, and here will be on negative side. Okay, so missed here. So this n minus 1 factorial, this n minus 1 factorial, and this n minus 1 factorial will cancel from both sides, and then you will get minus n minus 1x. Here minus sign is missing, so unfortunately minus sign is missing here, but you when you practice it, you should put minus sign before this term, and that will be ln this ln prime x by n. N is will be there, so this, and from this it will be like this, and from this relation you can finally get ln prime x minus n ln minus 1 x plus n ln minus 1 prime x, and this is this equal to, since all these terms are taken in one side, so that will be ln prime x. Okay, and then minus this will come here, n into ln minus 1, and that will be a plus sign, and this will be a negative sign. So that is what you can write ln prime x, that is equal to ln prime x, that is equal to this will be positive sign n into ln minus n, and here will be a negative sign. That is here you should put a positive equal sign. If you use here a equal sign, then that this will be, that is ln prime x is equal to this and this. Here it is not negative sign, it is equal sign. So this is one of the most recurrence relation. Also from equation 2, that is from equation 2. Where is the equation 2? This is equation 2. This is equation 2. That means and you have to use this this value. So equation 2, also from equation 2 you can write, obviously here is written once again, e to the minus x t this 1 minus t n is infinity ln x t to the 10 by n factorial, that is equal to omega. So differentiating with respect to t, differentiating this equation with respect to t, and in this case we use this and this term, these two terms. So del omega del t, that is del 2 is infinity, then integration of this, the differentiation of this with respect to n ln x t to the n minus 1 n factorial, the minus the second term is this. So that will, so it will go to infinity, and in this case the term was t to the power n plus 1. So differentiation of that will give you n plus 1, then ln x t to the power n by n factorial. This is equation 10. And from equation 5 we have in equation 5 that 1 by omega del t, that is equal to minus x 1 minus t whole square, and from here you can compute del omega del t, that is del omega del t as minus omega x by 1 minus t whole square, and using the value of omega from this relation, this is omega is equal to this, you finally you will get del omega by del t, that is equal to minus x 1 minus t somewhere in equal to infinity ln x by n factorial to the power n. This is equation number 11. And now just compare equation 10 and equation 11. You will have what is written here. Here, just compare this equation 10 and 11. You will have this is equal to this and this. Just separate these two terms. These two terms from here. These two terms. So that so finally comparing these two equations 10 and 11, you will have this. And after simplification, there are the method of simplification is given here. Just go through all the lines, all the steps. No steps are missing here. Everything is clear. Every calculation is given here. Due to the constraint of time, I only finally write what I have obtained from the calculation given in these two lines. And here is the term x minus x n is equal to infinity ln x n factorial to n, that is equal to 1 minus t n is equal to infinity ln x t to the n minus 1 n minus 1 factorial, and these two terms. Just concentrate and do the calculations and follow what I have done here. Just follow this. All the calculations are given here. I think there will be no problem to understand this. And now after simplification, here are some other steps. Just go all these steps. Everything is clearly stated here, clearly done here, and I assure you that there will be no problem to understand all these calculations. And after all these calculations, you will get this line minus x ln x, that is n plus x minus n into ln x, and minus n plus 1 ln x plus n square ln minus 1x. And from this relation, just simplify is, and that this will give you. But here is a mistake. This plus n will be minus sign. So this is here, and then x minus 2n minus 1. Here will be minus sign. ln x plus n square ln minus n x, that is equal to 0. And this is another important recurrence relation. So this relation, to get this relation, to obtain this relation, you have to perform some calculations. Those calculations are given from here. From here, just go through these lines, and it ends at here. So just keep your mind cool and calculate this, and I think there will be no problem. And this is another relation. Okay, now come to the last topic, that is orthogonal properties of ln x. And in case of Lagurre polynomials, Lagurre functions, there are two orthogonal properties and satisfying by the Lagurre functions, and these two properties are stated here, given here. Number 1 is 0 to infinity to the minus x ln x dx is equal to 0, where m not is equal to n, and the number 2 is 0 to infinity e to the minus x square ln square x dx, that is equal to factorial n mod whole square when n is equal to n. And we are here to prove these two orthogonal properties. And to do this, as we know that, or we consider that y is equal to ln x is the solution of Lagurre equation, and then substituting ln x instead of y in Lagurre equation, and we will then get x ln x by dx square plus l minus x d ln x dx n into ln x that is equal to 0. This is equation 14. And if we multiply both sides of this equation by e to the power minus x, then you will get this line. So there we obtain this line by multiplying this equation by e to the minus x, and these two terms, this can be written as dtx of e to the minus x x d ln x dx, and if you compute this, the whole term, entire term, these two terms will come, and after that n e to the minus x ln x, this is equation number 15. And similarly, if you consider that y is equal to lmx is another solution of Lagurre equation, then in accordance with this equation, you can write dtx of e to the minus x x d lmx dx, that is plus, and after that plus m e to the minus x lmx, that is equal to 0. In this case only replace n by m. Okay, this is equation number 16. And now multiply equation number 15 by lm, and then equation number 16 by ln, and subtract the second one, that is after the multiplication of this term with ln from the multiplication of this term with n. So just multiply this equation by lm, and then this equation by ln, and multiply and subtract the second one from the first one. Then you will have, here is lm first, if you multiply this, so lm is here, dx e to the minus this term is there. Okay, and then from here, since you are multiplying this by ln here in this case, so ln is there, ddx of this entire term is there, and after that this after that, since it is multiplied by ln and this is multiplied by ln, so you can write is as n minus m e to the minus x lmx ln x, that is equal to 0. Now what you have obtained in this expression, that is given here, and integrate this equation, all the terms of this equation, that is or integrate this equation with respect to x from 0 to infinity. And if you do that, then you have this expression from here, that is 0 to infinity ln dtx e to the minus x, then x ddx ln x, and this after that integration of this term is here dx, and then n minus m 0 to infinity e to the minus x ln x dx, that is equal to 0. So the term we are here, we need to compute this term and this term first, and so the first term is written here, this is there, and you can write this as the integration of this will give you, this is partial differentiation, this is a term, and this is another term, and this the partial differentiation is given here, this is and that will give you the first term as ln this, and just differentiate this in just integrate this term. So that will give you this, and this is 0 to infinity, and 0 to infinity x to the minus m dlm x ln this is done here, this is written here. And similarly lm ddx of the second term, so this can be written as the first term, if we use the value of x is equal to 0 first, and this value will give you 0, and if you use x is equal to infinity, from this it will also give you 0, so this term actually eventually becomes 0. So this, that is ln 0 to infinity ln ddx x e to the minus x ddx ln x, that is equal to 0 to infinity with a minus sign x e to the minus x dln x dx dln x dx, that is equation number 18. And the similar manner, you can find out the value of the another term, that is this term, this term. So this is written here in the similar manner, 0 to infinity ln ddx of x e to the minus x ddx ln x, in equation number that is given in this expression, that is present in that expression, will be minus 0 to infinity x e to the minus x dln x dx dln x dx, that is equation number 19. So then from equation this term and this term will cancel each other, and then from equation number the only term there will be is this, only this, because these two terms will cancel each other. So finally we get n minus m 0 to infinity e to the minus x ln x dx x dx, that is e to the minus x ln x ln x dx is 0 to 0. And in this case, obviously m not is equal to n. Or from here 0 to infinity e to the minus x ln x dx, that is equal to 0 for m not is equal to n. This is the first orthogonal property of the Lagurre polynomials or Lagurre functions. In this case, obviously m is not equal to n. Now another for the another orthogonal property, orthogonal relation, we just have to recall the relation. This type of relation has been calculated. Just see here, see here, see this recurrence relation. I told you that this sign is negative, so use this relation, use this recurrence relation with negative sign is here. So just to recall this relation, because this recurrence relation that is here, we call that relation that is equal to this. So now replace n by n minus 1 in this expression. So it will give you first term ln x, then x minus 2n plus 2, and because minus 1 is there, so plus 2, then minus 1 ln minus 1x plus n minus 1 square ln minus 2x, that is equal to 0. And from this you can easily find out, easily go to this line, that from here you can get ln x, x minus 2n 1 2n plus 1 ln x ln minus 1x, then n minus 1 whole square n minus n 2x, that is equal to 0. This is equation number 21. Now multiply equation 21 by ln x, that is the just multiply this equation by ln x, and equation 20, that is this is equation 20, by ln minus 1 x. So multiply this equation by ln minus 1 and multiply this equation by ln x, then what we will get, the first term, that is if you multiply this equation by ln x, then you will get this. Just look at this. This is nothing, only here multiply this equation by ln x only, that is here, and multiply this equation by ln minus 1, that is done here. Just look at this, all this term is written here, and after subtracting the second one from first one, that will give you ln x square minus ln plus 1, and all this term, all the calculation is given here. Just look at and compute it, and there is nothing missing, every term is given here. And after that, now you get these ln square x, ln plus minus ln minus ln plus 1x, ln minus 1x, then plus 2 ln x, ln minus 1x plus n minus 1 whole square ln x, and then ln minus 2x minus n square ln minus 1 square x, that is equal to 0. Now multiply this equation with respect, multiply this equation with e to the minus x, and then integrate it with respect to x from 0 to infinity. Then you will get from the first term, see here 0 to infinity to the minus x ln square x dx, then minus 0 to infinity to the minus x, this term is written here, and dx, then this term 2 into this term is written here, and after that the final term is n minus, see here n minus 1 whole square, this term is also here given, and from here this term is here. From this term you have obtained this term. Now according to orthogonal property, you know that in this relation 0 to infinity to the minus x ln plus 1 x ln minus 1x, if it is m and it is n, so in this case m not is equal to n, and this value will give you a 0 result, that is written here. And also from this n, and it is n minus 1, these are different values of n's, so this will also give you null result. And from here also this is n and this is n minus 2, so in this case two n's are not equal, so this will also give you null result. So this term and all this term will give you null result, that is written here according to the first orthogonal property. So you get from this relation, this expression, finally you get n square, it is written here that the first term was 0 to infinity to the minus x e to the minus x ln x square ln square x dx, and then minus n square 0 to infinity to the minus x ln minus 1 square x dx. So from here you can write this, the left hand side, that is equal to n square into this. And now very interesting thing is inherited in this relation. Just look at here, you are here that you are computing these value. this value, and the result of this is the power of the order of the, what is the order of the polynomial? Here is n. So here that n square is given here. So this term is nothing but the order square of the order of the polynomial. So that is done here, and then 0 to infinity e to the power minus x, and here is the polynomial of order n, and in this case this n should be replaced by one order lesser than it. That is, for the next very term it will be n minus 1. So that comes here. So it is l n minus 1 square x dx. So if we go to the next term, that then what we will have, we will get n square for the first term is here, and we know that this n minus 1 will be decreased by another one. So l n minus 1 will then be n minus 2. So here see that this n square is here, but in this case, since l n minus 1 is n minus 1 is here, so here will be n minus 1 whole square, then 0 to infinity to the minus x, and this will decrease by 1, so ln minus 2x dx. And the very next term will be, these two terms will be here, and then this n minus 2 whole square will be there, and 0 to infinity to the minus x, and this will be decreased by another one, so ln minus 3 square x. In this way all other terms will be come, and this will go until n becomes this number becomes n. This number becomes n, and in that case this term all will give you n square, n minus 1 square, n minus 2 square. In this way it will continue up to 1. And so that is written here 1 square, because you see that here the term is n minus 3, and this ends one order before that of this. So since it is 0 the last term, so here will be in this is the last term will be one order before than that of this, and before of this the order was 1. So the last term here is 1 square, and e to the power minus x l0 x dx. So it is very interesting to come in this expression, and then you know that n into n minus 1, n minus 2, in this way dot into 1 will give you n factorial. So all this term will give you n factorial whole square, and then e to the minus x l0 square x dx, and you know, or you already computed that l0 x is equal to 1. So if you use this, so that will give you n factorial square 0 to infinity to the minus x and dx, and that will give you n factorial square, and the integration of this will be minus e to the minus x 0 to infinity, and if you use infinity then it will give you 0, and for 0 it will give you plus 1. So that is equal to n factorial, and therefore you finally obtain 0 to infinity to the minus x ln square x, or better it is right, can be written as mod ln x, that is equal to n factorial whole square, or mod ln factorial. This is the orthogonal property number 2. So we in this case can easily find two orthogonal properties obeyed by in the Lagurre polynomial equation, and this is the end of this series, or end of this chapter, or end of this class. And students, you are requested to practice more and more, because it is completely a mathematical part, and if you practice more and more, all things will be clear to you. And I am just ending this class here.